Welcome back to Module 3, Traveling Math, Part 2. We're going to be covering sections 6.4 and 6.5. The nearest neighbor and repetitive nearest neighbor algorithm. So remember we talked about two strategies, brute force, which we covered in the last video, and the nearest neighbor. So the pros and cons of the nearest neighbor. The idea is you're going to hop from vertex to vertex using just the simple rule from the starting point. What's the nearest vertex? And from there, choose the next nearest vertex and repeat. Now, we do want to pick the nearest one that's the least cost. So that's really pretty much it. It's an efficient algorithm because it doesn't take much time, but it's not going to guarantee the best optimal tour because we're not going through every option. We're just looking at a small subset. So it's an approximate algorithm. Okay, let's look at Willie's the traveling salesman problem. The optimal tour on page 182, you end up finding out that the optimal tour costs $676. But when we do the nearest neighbor, we get $773. So let's do the nearest neighbor together. So we're starting at point A. The nearest neighbor, so I've got choices of 133, 152, 119, and 185. So the nearest neighbor that's the cheapest is 119. So then from there, I look at what are my next options. So I've got 174, 121, 120. So I'm going to pick 120. Now from there, I've got 133, 200, 119. Now you might be thinking 133, but that's going to close my circuit back to the starting point. And so I'm not going to do 133. So the next nearest neighbor is going to be 199. Now from that, I could do the 152, the 174, the 150. Now, I'm not going to go back to A because I haven't gotten to B yet, so I'm not going to do that one, but I am going to do 150, and that would have been the cheapest one anyway. And then from B, the only way back to A is that. So that is the nearest neighbor, and if you add all those up, you're going to get 773. So what is the optimal tour was not found, but that is exactly how you do the nearest neighbor. Way easier than brute force. So you can calculate the relative error. We won't be doing that in our problems in our project, but this is how you do the nearest neighbor. Again, you can pause it and review it. You start at the starting point, and then from there you pick the next closest one with the least weight, and you continue making sure you don't go back to the beginning until the very end. Now there's the repetitive nearest neighbor. It's just a variation on the nearest neighbor. So the reason that we would do the nearest neighbor depends on the starting vertex. If we change the starting vertex, then it's likely to be different. It's not unreasonable to repeat the process several times, each time starting at a different vertex. In Willie's case, we have to start at A because that's where he lives. But sometimes it doesn't matter where the starting point is, and so you can start at different places and get different nearest neighbors. So what do we do with a tour that starts somewhere other than the vertex we really want to start at? It's not really a problem because remember that in an abstract sense, you're starting where you end. And so really there is no start and end in a circuit. I know, mind blown. Okay, we're back to Willie. They've just removed some of the stuff. This is the path we just mapped out of the nearest neighbor. But if we use B as a starting vertex, the nearest neighbor tour takes us from B to C, and then to A, and then to E, and then to D, and then back to B. And that gives us 722, which is an improvement. It's a lot less. We could repeat the process again and again, and when you do this, you're going to get closer and closer to the optimal tour. And among all the nearest neighbors, the closest we get is 722. So how do you do the repetitive nearest neighbor? You might opt to do this on your project. You just start at any point, and again, it won't really work in the project because you have to start like Willie, but finding the nearest neighbor, you calculate the cost of that tour, and you repeat the process with all of the vertices. And that's how you do it, and the least cost wins. The last thing we're going to talk about is the cheapest link algorithm. The idea behind it is to piece together a tour by picking the separate links or legs based on cost. So it doesn't matter if in the immediate stages the links are all over the place, like if we're building a tour that doesn't connect, but there's some rules we can follow and they'll come together at the end. So this is how it works. We're going to look at the entire graph and choose the cheapest edge of the graph. So step 1, choose just the cheapest edge. And once that's done, choose the next cheapest edge, whatever that may be. Now there's 2 rules we want to be careful of. Don't allow it to form a circuit except at the very end, and don't allow 3 edges to come together at a vertex. So what that means is you can't have, this is your vertex 1, 2, 3. That will create a problem. So as long as you follow that rule, it will come together at the end. Okay. So among all the edges of the graph, the cheapest link of this is AC, right? 119 is the cheapest link. So we've got 119. Now what's the next cheapest link? Is CE, that's 120. So far they connected and we got lucky. But now we're looking, we've got 119 and 120. The next cheapest link is BC. But the problem is that coming out of C, if we did that, see how there would be 1, 2, 3 legs, 1, 2, 3, and we don't want to do that. So we're actually going to cross off that 120 leg because that's not possible anymore because it will create that 3rd edge. So then the next cheapest after 120 would be 133. See how they got rid of the 121? But the problem with that is that's going to take us back to the starting point and we're not ready to end yet. So we can't do that either. So now we're back here. We've eliminated those other links and now we're looking for the next cheapest. And the next cheapest is 150. Now you may be thinking, well, that's not connected to anything. That's okay. You're just building the cheapest links, not worrying if they connect. So now we've got our cheapest, our next cheapest, our next cheapest, and then we've got 152. And again, it's not violating any rules. There's only 2 edges coming out of D. We've hit all the other vertices, so it's fine to go back. And so it actually ended up building a link all together, formed a circuit. When you add it up, you get 741. It's a little better than the nearest neighbor, but not as good as the repetitive neighbor. So again, the optimal is always going to be brute force, but we're trying to find other options so it's not as time consuming. So how do you do the cheapest link? You pick the cheapest link, you mark it, you pick the next cheapest link and mark it, and you just make sure you don't close the circuit and you don't create 3 edges out of a vertex. Connect the last 2 and close the circuit. So we've got these 7 sites on Mars, and we went ahead and changed it up. Now again, it looks really different, but these are all the different distances in between the graph. So if we wanted to do brute force on this, we would have to do 720 different tours. So I think that's going to be a pass. Cheapest link is reasonable, but it's not too hard, so let's take a peek at it. So for cheapest link, we're basically looking for the smallest numbers first. So we've got the smallest number that we see on here is 1300. And that's PW. The next smallest number is 1500, and that doesn't violate any rules. Now we need to be careful. P already has 2 lines coming out of it. We cannot add a 3rd. So this one we did, this one we did. IN would be the next one, so that's 2000, and that doesn't break any rules. Now AW, if we were to do AW, it would create a circuit. Do you see how it would close that loop? And we don't want to close any loops. So we're not going to do AW. The next 2 that we're going to do is HW and AI. And again, we're not breaking any rules. Now if we do IW, what happens? We get 3 out of I. We don't want to do that, so we have to not do that link. Now IP has the same thing. We can't do IP, but we can do GH. And then GN is going to close our circuit. And then by using the cheapest edge, we were able to get it really quickly and create a loop and get our total length. The nearest neighbor algorithm, we could do the same thing. So let me grab this guy for you. Let's copy this. Okay. All right, so if we start here, if we start from A, the shortest nearest neighbor would be AP, and then we would go to W because that's the least edge, and then we would go to H because that's the shortest out, and then to G, and then to I, and then to N, and then back to A. So that would be our nearest neighbor. And that's going to give us about 20,000. And our cheapest link just gave us a little bit more. So in this case, the nearest neighbor actually worked a little better. So the first surprise is that the nearest neighbor actually gave us a better one than the cheapest link. So sometimes the cheapest link produces a better tour, but that's why we call these approximate algorithms. Again, the one that's always going to work is brute force, but when you have too many vertices, you just can't do it. So that's the end of the Hamilton circuit unit at the traveling salesman problem. You guys in your project are going to complete one as well.